Okay, hi guys. So in this lecture, I'll be talking about conformers. So let's start with this conformers. There's a O between. Okay, conformer. Let me rewrite it. So it is okay. Okay. So conformers are just the isomers formed by the rotation across sigma bond. So isomers formed due to rotation across sigma bond. Okay, so there are infinite conformers that are possible because we are just um, rotating the groups attached. Different groups are substituted attached on the carbon atom or in a different atom in an organic compound. So there are infinite number of isomers possible. So across a sigma bond. Okay, so now next comes is means from where do the energy comes in for the CC bond rotation. So for that answer, the energy is available at room temperature, and all the conformers can avail that energy and can use it to form various kind of different isomers, but by rotation across their sigma bond. So energy needed for CC bond rotation is available at room temperature. Okay, so let us take some examples for the same. So suppose I have this organic compound. So I hope you are seeing means how the structure of the carbon atom and all of the atoms attached to the carbon atoms is. So this plane, this bond is in the same plane. So this carbon atom and this carbon atom are in the same plane. Now when I draw this H, so H is towards you, towards your face, or um, emerging out or seeing out from the screen, and this H is going into the screen or going away from your face, and this is the hydrogen atom uh, which is perpendicularly south to this bond, or it's down to this bond. Okay, and for this hydrogen it is again away from the your face, and this hydrogen is looking towards your face, and this is in the same plane as carbon and is below the carbon atom, this hydrogen. So this is how we make it. Okay, so this is called a Sawhorse projection. Sawhorse projection. Let us look at another example where we have a circle, 3 hydrogen attached here and 3 hydrogen attached here. So this is the same compound as the previous one, and this is called Newman projection. So if you look closely on this compound, or what is the explanation of attaching this hydrogen on the circle? So this signifies that this is the first carbon atom and this is the second carbon atom. So on the first carbon atom we have 3 hydrogen groups attached here, here and here, and on the second carbon, for the second carbon we show it as a circle, and on the second carbon we have 1, 2 and 3 hydrogen attached. So let me number this. So if I number this is 4th, 5th and 6th hydrogen. So this is 6th hydrogen, this is 4th hydrogen, this is 5th hydrogen. Okay, so let's suppose you are facing here, you are looking here from this angle. From this angle you can see that this fourth hydrogen would be something like this, and this fifth hydrogen would be something like this, and sixth would be down. Okay, this is the Newman projection. And if I make something like this, if I make in Sawhorse projection, if I make uh, hydrogen atoms oppositely attached to each other, then or at 180 degree to each other, then it is this conformer is called staggered, where the bond angle between the first carbon hydrogen and the second carbon hydrogen, which is corresponding to the first carbon hydrogen, is 180 degree. So this is called staggered configuration or staggered conformer. Okay, and if we have both, the angle between both is 0 or 360 degree, let me redraw it, then the angle between the carbon hydrogen atom of the first and corresponding hydrogen atom of the second carbon is 0 degree, then this is called eclipse conformer. So this is the Sawhorse projection of the eclipse Sawhorse. And what would be the Newman? Newman would be something like, for the first carbon this is the case, and what second carbon, I just draw a circle and just make this slightly separated distance so that it's good for a human eye to see that on paper. Okay, so let us draw some Sawhorse and Newman projection and diagrams for the following compounds, and you will understand, and with more practice you will be able to draw Sawhorse and Newman of the following compounds. Sawhorse and Newman. Okay, so let's say I have compound something like this, and CO2H. CO2 is attached as so the angle between CO2H of first carbon and second carbon is 180 degree. So what would be the Newman? For Newman you just have to be here, see from this side. From this side you can see that on the first carbon you have H here, OH here, and CO2H here. Then you look at the second carbon, you draw a circle, you draw a CO2H here, one H here, and another H of the another OH of the second carbon, like this. So this was staggered. Okay, so second example, we have H, Br, so what would be the Newman for here? For this case, H, draw a circle, yes, CS3 here, Br here, H here. How do you arrive at it? You are looking from this side. Okay, now what happens here? So on the first carbon, if you look from this side, you have D here, you have H here, and you have phenyl ring here. On the second carbon, what do you see? You have H here, you have D here, and you have pH here. So it is a eclipse structure. Okay, so now you have to draw the conformers of N-butane. So coming to the next question, you have to draw conformers of N-butane. Based on C2 and C3 bond rotation. So we would have something like, this is N-butane. We have to draw the conformers of the following. Okay, so we'll be drawing various conformers. So let me start from the first one. So first would be, if I have H, so this is the first carbon I am seeing. Oh, sorry, we have to do on the basis of second and third carbon. I am extremely sorry. Okay, so between this bond you have to rotate. Okay, so you can see that one of the way of drawing it is, let me not draw that bigger bond, H here and CS3 here, and for the second carbon I can have H in the same position as CS3. So this is called fully eclipsed. Carbon carbon bond angle is 0. The substituents the bond angle between the substituents of first carbon atom and the second carbon atom is 0 degree, hence this is called fully eclipsed. Okay, second is when we rotate the second carbon atom by 60 degree, we would have something like HCS3 and rotate it by 60 degree. So we would get H, rotate this by 60 degree, then we would get HH and CS3. So the bond angle between substituents of first carbon atom and second, or the second and the third carbon atom, is 0. Okay, so this is called Gaussian form. Okay, in the third example, if we rotate it again by 60 degree, then we would have something like H here, CS3 here, and another H here. So this would be partial eclipsed. Bond angle between C2 and C3 is 180 degrees, so this is partially eclipsed. Okay, now let us take a fourth example in which we again rotate this bond angle with 60 degree. So this would be staggered. So we had H and CS3 on the first carbon, and on the second carbon we would have something like CS3 here, H here, and another H here. So bond angle between C2 and C3 is, we can imagine, 180 degree. So in this case I actually wrote 180 degree instead of 120 degree. So this is called staggered. Okay, so let us look at why eclipse structure is unstable. So by eclipse I mean the first one, fully eclipsed. Why the eclipse is unstable? Why? Because you can see two bulky groups very near to each other from on the second carbon atom and on the third carbon atom. So due to the presence of van der Waals strain, there is a repulsion between these two CS3s, hence eclipse is unstable. So due to van der Waals strain. Okay, okay, and second reason is there is a torsional strain which is also called bond repulsion. We'll not go into detail of that, but obviously you can remember if you can. So the first thing is this, second thing is due to torsional strain. Okay, so this is out of scope for this series of video lectures, and it's not very important thing. You won't be asked, means you may be rarely and very rarely asked question about this, but I don't think this is as useful for the JEE perspective as other important things are. Okay, so basically it's a bond repulsion thing, bond repulsion, due to which there is a strain in getting the atoms rotated across a sigma bond. Okay, so what would be the relative ordering of stability order? So just look into it, that relative stability order. So the relative stable order will be first staggered. Why? Because two bulky groups are 180 degree apart from each other, opposite to each other. Then comes Gaussian form. Why Gaussian form? Because still in the fully eclipsed form, still there is a repulsion between hydrogen and the CS3 groups. It is less than fully eclipsed, but still it is there. So Gaussian would be more stable. Why? Because it is at a distance away from both CS3 and H. So then comes partial eclipse, Gaussian. Then comes partial eclipsed. Then comes fully eclipsed. Okay, so with this we come to an end of this lecture. So in the next lecture we'll be comparing on a graph all these conformational structures, and we'll look into some more things like dihedral angle, rotational barriers, and things like that. So till then, good luck and goodbye.